and then we'll admit everybody. Give it a couple seconds here. Nancy, did you admit everyone? What happened to the people we had in the lobby? I don't see them. There we go. Okay, welcome everyone. We'll just give it a couple minutes while people join. We are admitting folks into today's webinar. I see Armando. Armando, always great to see you. Been a while. All right, well, I'll get things kicked off and do some housekeeping, but special welcome from Aaron Smith and Nancy Bakeman with the Energy and Environmental Building Alliance and our webinar podcast series. And we have a great friend of EEBA here today, Robbie Schwartz with Build Tank. Many of you know him and love him. Great building science expert. Always at the summit since I've been at EEBA. Will be with us in Salt Lake again this year. And I think today's topic is extremely relevant. We actually went through 2021 IECC and Zero Energy Ready Home Program this morning with the Builder Benchmark Group and EEBA. I think you're starting to see codes lean more this way or be pushed this way to the 2021 IECC. So hopefully there's a lot of great questions. Put those in the Q&A. I'll ask them to Robbie throughout. But Robbie, from Nancy and I, welcome. And thank you for joining us today and educating us more about all the great changes that are coming.
Well, I appreciate the opportunity and thank you very much for having me. One of the reasons I am really interested in this topic is that I believe that there's a lot of building science wrapped into the code. And I get really frustrated when I hear that building to the energy code is the ability to build the worst performing house that I'm legally allowed to do. And I just don't think that's true if you're building to the actual code. The big issue there is how the code is actually adopted and amended and implemented in each of the jurisdictions. So,
but Robbie, I think you're right. We're at a point in time, we had this discussion this morning where the 2021 IECC is, we think, going to be pretty broadly adopted. And it is a really good code in the general sense of the term, right?
Yeah. If again, it's adopted with minimal amendments and whatnot, right, and actually enforced. So that's what I hope to kind of demonstrate today. So I'm just going to jump right in here. I'm going to leave I usually turn my camera off, but I'm going to leave it on, and you might see kind of the side of my head because my main screen is over here a little bit. But we're going to talk obviously about the building science and kind of an intro into the code, how building science defines the building thermal envelope, or how really the energy code defines the building thermal envelope. And then we're going to jump into the 4 control layers as a means to kind of get at the building science that's in the code. So from this perspective of introduction, really our modern day times and the expectations that we have of our houses have changed the way that we build our houses, and hence the need to bring building science more into code. A simple example is that house on the left here that was built in 1910. And if we think about our notion of comfort in 1910, our grandparents might have been in that house. They were really willing to put on a sweater in the wintertime, maybe shovel some coal, put a log on the fire to maintain comfort in the wintertime. In our modern day houses built in 2020 or 2023, we literally want to be able to walk around in our underwear from room to room and floor to floor and be comfortable. And in Northwest Denver where I live, we're scraping all these old houses, adding these new houses, and we have to figure out how we're going to build houses that are going to meet their expectations, but also be durable, be able to last that 100 years and whatnot. So, the biggest thing we know is that these older houses are drafty and comfortable, yet they're very, very durable. And the primary reason they're very durable is that they have tremendous drying potential. And so as we insulate and we tighten up houses, we're building houses to meet that modern day expectation. We need to make sure that we have proper moisture flow through our building assemblies and proper drying potential. And that's kind of why we're going to be focusing on those control layers and the building science there. But from the basics of applied building science, we're really focusing on airflow, heat flow, and moisture flow, and ultimately getting control and predictability of those assemblies that are governing moisture flow, heat flow, and thermal flow in our houses. And we're talking about the structures, the systems, the enclosures, the climate that house is built. But the big wild card that kind of the science helps us govern, that the code might not look at itself, because the code is looking at structure, the code is looking at systems and enclosure and climate, but the code doesn't integrate people and the crazy things that people do to houses. So the building science and incorporating the building science into the code is that ability to say that if I've built a house for a retired couple of two and the contract falls through and a family of 6 move into that house is still going to perform regardless of the crazy things that people do in that house. And like I was saying, the code does govern climate, and climate is a huge issue from a building science perspective. We do things in different climates differently, and the code puts out this climate zone map. And we should note that in the 2021 IECC that the climate zone map has changed. The climate zones, the warmer climate zones are moving north in essence there. So climate zone 3 and 4 have creeped a little bit further north there. And then we have the big dividing line in the middle that's dividing the dry climate zones and the moist climate zones from us. And here in Colorado, we have pretty much all the climate zones except for the marine climate zones there. So, we have to understand what we're going to do on the plains versus what we're going to do in the mountains versus what we're going to do in the far southeast corner of the state there. So it's important to know those climate zones and make sure that we're going to use it. Now, when we talk about these control layers and kind of the building science that's wrapped into the code with each of these control layers, they're usually listed in order of kind of importance, from bulk water, rain control layers, to air, because of the amount of moisture that moves with air, to vapor control, to thermal control. And I'm going to describe them from a code perspective, starting with the thermal envelope, vapor, air, and bulk water, because you'll see that the code, especially the energy code, has this kind of myopic focus on the building envelope and really protecting the integrity of the building thermal envelope there. And then it goes into vapor, air, and bulk water there. So the thing we should know about the code is that it's intended to provide flexibility. And the flexibility comes into the code when you're talking about different compliance options that the code allows you to. So it turns out that builders, especially custom builders, tend to myopically focus in on the R value table there, but the R value table is basically a thou shalt do approach to code, and it doesn't give you the flexibility to do what we call trade-offs, which I'll explain off here a bit. So we need to read the code like you would read a program checklist from Energy Star or the DOE Department of Energy and see the flexibility. So I like this statement from the Dalai Lama, because if we understand the checklist, if we understand the language of the code, we can learn the rules and we can figure out how to break them properly and still build a house that we're comfortable with building in terms of the assemblies and systems that we're using, but be able to build it that meets our cost expectations or other performance expectations that we might have. So when we begin to look at the code, we have to first kind of choose that compliance pathway. And that's really kind of a paperwork exercise to tell the code official how we're proposing to build the house to meet the expectations of the code or the requirements of the code there. And that's kind of twofold. One is kind of the energy use that's happening, and that's why we begin with maybe some type of energy modeling, and then the actual installation requirements that are kind of laid out in that section R402 through R404. Okay, so these compliance pathways revolve with two compliance pathways that are in the prescriptive section of the code, the U value and R value table, and then the prescriptive compliance UA compliance option, and then we get into performance compliance options. And in the 2021, they added a tropical zone or tropical climate compliance option. In addition, in the 2021, you have these additional energy efficiency requirements that you have to choose. You have some choice of what you choose, but you have to do some level of additional efficiency that revolves around building a tighter envelope or adding higher efficiency mechanicals or bringing all your duct into conditioned space. You have some choices there. But really getting into the compliance here, again, the prescriptive U and R value table don't give you any options or flexibility in how you're going to build that house. But these three pathways that utilize a software, they do start giving you some flexibility and some options to be able to do what we call trade-offs. And these three options utilize the additional energy efficiency packages a little bit differently. The prescriptive pathways have you choose from these specific options. The total building performance says that you basically have to build about 15% better than you normally would have to build to, and the energy rating index kind of follows that same notion there. So what we're getting at here is that the energy code is starting to adopt energy modeling as a means to demonstrate compliance. And the best thing from the perspective of energy modeling is that energy modeling allows you to fail fast and fail on paper so that you can succeed faster and meet the requirements of the code. And so basically what an energy model does is that we build the geometry into the house. Into the energy model software there. And the energy model builds two houses that are geometric twins of each other. We have the reference home and we have the rated home, or sometimes called the builder's house. And the builder's house is compared to that reference home in order to demonstrate compliance. Now, the specifications for the reference home are defined specifically as a standard set of house specifications that generate a specific, a consistent, and a quantifiable amount of energy use. So the code reference home is overlaid with the U value table when you're using the area weighted U value process, or a table that is built into the code in section R405 that defines the reference home. But in essence, the reference home, if you built to the reference home, exact standards of the reference home, you would have a house that is a standard set of specifications that derives a consistent and specific amount of energy performance for that house that is deemed to be what the code is asking for, what the code is requiring us to do. So why we use the software is I want flexibility in how I'm going to specify and create my house as a builder. So I could maybe not put in the code required R value table requirement for the attic insulation and still have a house that meets that specific quantifiable energy performance. So I want to be able to model that and compare the rated home to the reference home and see if I am equal to or better than the performance required by the reference home to demonstrate compliance there. So again, they're geometric twins of each other. One is overlaid with the code compliance specifications. One's overlaid with what the builder wants to do. in that house. And we have a variety of different reference homes that can demonstrate compliance with the code, with the 3 energy modeling approaches that are used in the code. But you'll also see that there are reference homes in these softwares that can demonstrate compliance with Energy Star or other programs that utilities might have. In its basic way, we have that reference home. Again, they're geometric twins of each other. Again, the reference home is overlaid with the prescriptive U values that are in the R402 table. The builder chooses whatever specifications they want to use. And in essence, the builder's house has to be better than or equal to the reference home in order to demonstrate compliance. And again, this gives us flexibility to do what we call trade-offs, which is basically putting something more in one location so I can put something less in another location and keep a balanced energy equation that is deemed to be compliant with the code. So in this way, the energy modeling could say that in climate zone 5, the blue ball might represent attic insulation of R38, when the requirement by the R value table says I have to install R60 attic insulation. And I'm, as a builder, say, no way, I've never put that much insulation in my attic. And we can say, well, that's perfectly fine. You just can't use the prescriptive R value table to comply with the code. You have to move to an energy modeling approach and demonstrate that you put maybe 3 silver balls or 3 other things in your house that would represent maybe better windows that you might already be doing, maybe a more airtight house or tighter duct system or more insulation someplace else. To trade off the less R value in that attic. So that's how we get flexibility. That's how we get the ability to figure out what's really the most cost-effective way to build a house that meets the requirements of the code there. Okay, so that energy modeling part is really all building science and getting it in there. So we're going to move into the thermal control layer, because you'll notice that the code is, again, focused heavily on the building thermal envelope. It doesn't really address mechanical efficiency at all until the 2021, where in the additional efficiency options, one of the options is to put more efficient mechanical equipment in the house. But in the past, you could still, and even now, you could still put in an 80% furnace, and that's fine, but they want to ensure that the thermal envelope is sound, and ultimately it's based off of how energy moves in our house. It always moves from higher concentrations to lower concentrations. So from inside to outside in the winter season, from outside to inside in the summer season, and the energy code gives us an idea of, when we're designing our HVAC systems, what the inside temperature is for that design, because it's defining the delta T temperatures in which that direction of energy is going to move in the wintertime and in the summertime. So again, dealing with this building science here, and the movement of energy and how it's conducting through our building thermal envelope. And what we know, and the rationale here, is that our HVAC systems will not work unless our building thermal envelope works. And that's one of the biggest reasons we have so many HVAC complaints in our homes. It's not necessarily that the HVAC system wasn't designed properly or working properly, but often it's because there are defects in our building envelope that we designed in. So let's say I designed that we're going to have an R20 bat wall, but those bats were installed so poorly that they're actually performing like an R10 instead of an R20. That's going to cause a big problem in our the ability for our HVAC system to work. So the building thermal envelope is defined kind of in a specific way in the energy code. You can see that it's an assembly of things: our basement walls, exterior walls, ceiling, roofs, and all these things. These assemblies coming together to give us a clear boundary condition between conditioned space and exempt unconditioned space there. So when we look at that, we can say that the energy code is really kind of looking at a belts and suspenders approach, where we have a primary interior air barrier, which would be the continuity of our drywall system, and we have a primary exterior air barrier, which would be the continuity of our sheathing material around the house. And if we have continuity of both, we have this belts and suspenders approach. And that's really kind of different, I think, than the way that a lot of builders will say, you know, I've got a clean exterior air barrier with my zip sheathing that's taped and whatnot, or I have a clean interior air barrier with my aero barrier system that's using the drywall as my air barrier system. And that's fine, but we can't forget that you're getting supplemental benefit from the continuity of the exterior. And you might be getting even more supplemental benefit by installing your exterior weather-resistant barrier, especially if it's a fabric type like a Tyvek or something. There, you're going to get a continued belts and suspenders over belt and suspenders approach here. And this is important to realize because when we get to the air side of things, the air barrier, air sealing table is really pointing out where we don't have continuity and where we need to add supplemental air barriers to maintain continuity, either on the inside or the outside of our systems. And from a thermal perspective, when we're using air permeable insulation, our ability to enclose cavity insulation to trap those air pockets and make that thermal insulation work and work well in those assemblies. Now, the next thing that the code does is it's basically adopted this red line test that Dr. Joe Stieberich kind of created that is pointing out these, first of all, the continuity of our air barrier and thermal envelope assemblies, but also where things connect to each other. And where things connect to each other are those areas where the greatest leakage is going to be happening in our home there. So the code says that the building thermal envelope shall be represented on the construction documents. If you were doing it with kind of the belts and suspenders approach, you would depict the building thermal envelope with 2 lines, but the code really doesn't say anything about that. It says basically just depict it so that the information can be sent into the field and hopefully help people understand the constructability of the assemblies that have been designed and made. Then the code goes on to describe the base R values that have to be put in each of the components assemblies that have been built here. And you'll see in the 2021 IECC that some of those R values have changed pretty drastically. But remember, you don't have to necessarily put R60 attic insulation in that assembly. You have to have the same level of performance as if you did, but you could trade that off for lower insulation. You could, builders are quite concerned right now about R5 continuous insulation. So you'll see here in Climate Zone 5, you have all these choices for how you can build your wall assembly and insulate your wall assembly. R5 continuous insulation is, that detail is hard for a lot of builders. Well, you might be able to trade it off, but you would have to move away from the R value table there. But you can see that they're setting a core expectation that we have a well-insulated building thermal envelope. And although you can trade off some of the R values in different components, you're still going to have a strong, well-performing building thermal envelope using any of the compliance options in the code there. So the last thing I'll say is that if you bought the first edition of the code, remember that it's difficult to print the code book accurately. So everything in red here is an errata, which means that it was misprinted in the first versions of the code. So you want to go and make sure that you pull down the errata and you understand what's actually in the code. You can do that on the online or just pull the errata there. But there is a free version of the code that's updated online. Now, just as a reminder, U factors describe the thermal transmission or the rate of heat transfer through a square foot of material, and R values describe the material's ability to resist the heat flow from more to less, or from higher concentrations to lower concentrations. And the U factor is the reciprocal of the R value. So if you have R5, it turns into a U factor of 0.2 there. And then assemblies are described by the U factor, and building components are described by the R value. But from a code perspective, the R value table and the U factor table are really describing the same thing. The U factor takes into account thermal bridging and what you would install in the components that the R value table is describing. And when you do kind of the math, you'll see that they basically are describing the same thing there. Now, in order to protect that building thermal envelope, in the 2021 IECC, some sections has been added in Chapter 3 here to talk about this whole new crop of insulation that's out there that doesn't have an R value mark on it. And if it doesn't have an R value mark on it, it's really difficult to understand how that insulation, or what the R value of that insulation actually is there. So what the code is asking for now is that the installer actually certify the installation and leave that certification at the time of install for the code official or a third party to come in and verify. So in essence, what they should be doing is actually some R value testing of their walls and whatnot to ensure that they're getting at least the R value, that the density of the blow is actually achieving the R value that they propose to put in to that house, instead of just estimating it or assuming that they're getting that. Whether that happens or not is up in the air, but at least we should be getting this certificate so that, in essence, you can hold somebody accountable for the R value that's actually installed in that building there. So again, in an effort to protect the building thermal envelope, this is what the code is doing. The other thing that we see from the code is that inspections for energy, we have to do all these different types of inspections there. And when you look at the code, you see that the inspections start to be narrowed into what is actually an energy performance issue there to help guide the construction or the code official field staff to inspect properly. So we're looking at the R values, and not only the R value, but has it been installed so it actually works in the assemblies? We need to look at those air barrier details, air leakage controls as required by the code here. And similarly on the mechanical sections, we're looking at required controls, system insulation and corresponding R values, system air leakage controls, so that's all the duct leakage part. Also, whole house control mechanical ventilation and minimum fan efficiencies and whatnot. So really, performance is becoming a big part of the inspection process there. So we can't go into a house and just say, yep, I see pink in the walls, and walk on to my next inspection. What we really need to ask the next question, yes, the product's there, but has it been installed so it's actually going to work in our assemblies that we're looking at? So the insulation's here, but you can see in the upper right-hand corner, for example, the insulation isn't actually touching the surface that it's intended to insulate. And at rim joists, that becomes even more important because we're not requiring that interior air barrier at the rim joist. That is one of the exceptions in the code. You have to have kind of that belt and suspenders approach in the above grade walls. But at the rim joist, it says specifically you have to rely solely on the exterior rimboard air barrier material there. So that means that we also need to make sure that the insulation is installed properly to make that work, and that we're getting the code required air sealing done to make that work. And just one last example, asking that question, simple question, is it there and does it work, will help our inspection process there. Now, the code also addresses some aspects of thermal bridging and the condensation that is created from thermal bridging. So we know that if 1 king stud is good, that 2 is even better, and maybe 6 is better, and 15 makes it even better there maybe from a framing perspective or an engineering perspective. But the reality is that we're over-engineering our houses, and often the framer is acting like an engineer and just adding a bunch of wood to the assemblies and making them just cold spots in our houses that create repeated wetting and condensation issues. So the code actually says that we should be reducing framings in two particular areas in that building thermal envelope. One is at corners, that we are supposed to have insulated corners, not only in the true exterior walls, but where interior walls meet exterior walls, some type of three stud corner there, or ladder blocking or something, to get our full insulation depth there. And we should also have insulated headers there. So we need to work with our framers, but we also need to work with our engineers to understand that this is a requirement of the code. And yes, there'll be an exception here and there where I've got to have, a true 3-ply header to carry the load. But in most cases, you can either go to a 2-ply header and push it to the exterior, or you can replace spacing material with foam board and get a system that works and works well and reduces that thermal bridging, reduces that cold spot that's creating condensation there. Yes, and we could even go to 24-inch on-center framing. We can go back to balloon framing that's exemplified here and get systems. The code isn't telling us we can't do these things. It's in fact really wanting us to do what we can do to make a sound building thermal envelope there, to reduce kind of mean radiant temperature and ensure that we have comfort inside of our houses there. And the last part with regards to the building thermal envelope is window to wall ratio. So that's the fraction of the above and below grade wall area that is covered by the fenestration. And there's a formula for creating that. And in the energy code, if your window to wall, window to floor ratios are up above 15%, you're starting to get dinged, which means that it's harder and harder to trade off if your window to wall ratio is high there. And the rationale is that windows are simply the weakest link in our assemblies there. If you did the kind of the area weighted R value calculation, and I assume that I'm building a really great wall because I'm insulating the cavity with R23 blown fiberglass, when I take into account the wood in that assembly, I drop that R value about in half. And then when I install a window that's anywhere from an R value of 2 to 6 there, I'm going to drop the R value even more. And the higher the window to wall ratio, the more the impact to the overall wall R value of that assembly there. So it's something to keep in the back of your mind. It's not something that's easy to get at. But one of the things that I think is important is to begin to talk to architects about proper design parameters around the placement of windows, and not just putting windows in to put windows in, but thinking clearly about how I'm bringing light in, how I'm maximizing views, but how I'm also protecting the integrity of the building envelope. One of those things that we can do is go to triple pane and double pane windows and get lower and lower U values in those windows assemblies here. And you can see that there's some great performance benefits to do that, but you also have some lower visible light transmittance, higher price, obviously, heavier units, things. But again, I think the performance characteristics really outweigh the downsides of going to windows. This is an interesting chart here that shows that the U value of the building assembly with the different windows that have been added, different R values of windows. And if you look at the orange line, if I have a window that is an R value of 1.1 or a U value of 0.9, it's that R30 assembly is really more like an R6 or so. And if I upgraded the window to an R5, my total wall assembly goes up to an R16. So again, you can see the impact of the windows in that assembly. So from a energy perspective, kind of building science perspective, our biggest bang for the buck is glazing, not going over that 15 to 20% window to wall, window to floor ratio, potentially putting less wall in the less wood in the assembly, and then thinking about air tightness and insulation of those assemblies there to make it work. Okay, so we're going to move on to the next assembly, which is our vapor control layer here. Now, the vapor control is designed to reduce the amount of moisture that is going to be able to get into our assembly, but it's only really addressing one process of vapor transport, which is vapor moving into the wall by the process of vapor diffusion there. So we can't, and we also need to continue to fight against the confusion that's out there about vapor retarders or vapor barriers, air barriers, weather resistant barriers. We need to be clear about our language so that we understand that what the vapor retarder is doing. If the vapor retarder is also an air barrier, we need to understand that. Is the weather resistant barrier ever a vapor retarder? Might it also be an air barrier? If we don't understand these things separately, it gets even more difficult when we start looking at them together and in unison. And the kind of the picture there kind of demonstrates that, because this applied air barrier is also potentially a vapor barrier and a weather resistant barrier. So we have assemblies out there that do all these things. What we know is that diffusion is a really small process of how water migrates from higher concentrations to lower concentrations to create equilibrium. This study was first done by Building Science Corporation, demonstrating that basically over the course of a heating season, a third of a quart of water moves through that assembly, a really small amount. Yet, from a code perspective, we concentrate on the vapor retarder traditionally much more than house tightness, and air leakage is that biggest, strongest mechanism that can carry water into our assembly. So we really need to concentrate on leakage in those assemblies rather than the vapor retarder, and promote drying over wetting of these mechanisms in of these assemblies, I guess is what I'm saying. So you'll see in the code when we get to the air leakage section that the code is asking us to seal these electrical boxes to the drywall to stop leakage, to use airtight boxes. And it's giving us mechanisms to stop that moisture from getting into the assembly in the first place. And again, the majority of the moisture is getting into the assembly by air leakage versus vapor diffusion there. And the consequence of that is potentially repeated condensation or wetting of the assembly once that moisture hits the cold exterior sheathing or that first condensing surface there. So we can use the psychometric chart or these other kind of knockoffs of the psychometric chart to give us an idea if we have air, typical temperatures in Denver, 70-degree air, that's 35% relative humidity. If it hits a surface temperature, whether that's a window or exterior sheathing, that's at 40 degrees, that moisture in that air is going to create a dew drop. It's going to create that condensation, and that repeated wetting is what destroys houses over time there. So the code says that we have to install a vapor retarder in our assemblies, but the problem is it doesn't give us any guidance. There are no manufactured instructions for how to install vapor retarders, and the only state in the country that really does it well is Minnesota. And I think because they primarily use that vapor retarder also as an air barrier, that they're making it work. But you can see here how often moisture gets trapped behind it because air leakage is moving moisture behind the vapor retarder, and it doesn't then have the ability to dry back out. So what is the code saying about water management here? We're using the vapor retarder to stop or retard the migration of moisture into the assemblies. We have all these materials that can be vapor retarders or some level of a vapor retarder. So we need to understand the materials, and we need to ensure we understand the materials so that we're not putting a vapor retarder on both sides of the assembly there. So that leads us to kind of this building science principle of doing what we call vapor profiling, where we're looking at the assembly and we're trying to determine what is the most restrictive component in that assembly that has the least drying potential in that assembly, so that we can promote drying in at least one direction, if not both directions, ideally there. So you'll see in this assembly that let's see, the closed cell spray foam is only 1 perm. So that would be the least, or actually the asphalt shingles is probably even less. We have less ability even to dry through that. But now that I know that, I want to make sure that I don't put an interior vapor retarder on this assembly if I'm building climate zone 5, for example, there. So that's the value of the vapor mapping here. When we start talking about vapor retarders, the energy code actually shifts us over to the IRC, or the International Residential Code there. And you see that language on the left side of the slide here. On the right side of the slide, we start getting into the IRC language that talks about the different classifications of the vapor retarder, and when we can install them and when we shouldn't install them. And one of the places that we shouldn't install it is on foundation basement walls. And in Colorado, we often insulate our unfinished basement foundation walls. So they're conditioned space, but they're unfinished, with a vinyl faced fiberglass blanket, which is a vapor retarder. So unbeknownst to a lot of builders, they're putting a vapor retarder in some place where they shouldn't, because they're trying to get separation of the insulation from the occupants, which is also required by the code. So we want to make sure that those materials have perforation in it that allows some permeability and drying to the inside of those assemblies there. Next, we get to this section of the vapor retarder that talks about the different classes of vapor retarders that can be installed. A class 1 vapor retarder has a perm rating of less than or equal to 0.1. A class 2 has a perm rating of 0.1 or less or than equal to 1. And a class 3 vapor retarder has a perm rating of 1 to 10. So it has the greatest drying potential. And in Colorado, we're trying to promote always using a class 3 vapor retarder. And it's turning out that in most climate zones, we're really trying to get to that class 3 vapor retarder to promote drying as much as we possibly can. And when we talk about drying, it's basically drying by the process of diffusion, that vapor being able to migrate out of the assembly by the process of diffusion here. So a class 1 vapor retarder are things like polyethylene, aluminum foil, sheet metal, those types of things. A class 2 vapor retarder, some of the rigid foam materials, but craft-faced batt is kind of the original Gore-Tex material. It stops moisture in one direction, kind of the smart barrier, but allows moisture to dry back out of that assembly. And then a class 3 vapor retarder, the biggest one that is used most often is latex paint, but you see a lot of the insulation materials are also some level of vapor retarder as well, in terms of their permeability of the product. And again, that's why we want to look at the vapor mapping of the assembly, because as you start layering in all these things, you could be creating a whole assembly that's a vapor retarder, or one that's more predominant or not. Now, this is new to the 2021. This chart here tells you where you can use which class of vapor retarder. And you can see class 3, you can use class 3 in all climate zones until you get into climate zone 4 through 8, where there's some caveats in order to use that class 3 vapor retarder there. So the other thing that the code talks about is spray foam and spray foam thickness in order to create a vapor retarder. And not only do we need the right thickness of the material, but we need to ensure that it's installed properly. You see the picture on the lower left here. That spray foam has not adhered to the studs or to the exterior sheathing there. So it's not going to work as an insulating material, and it's not going to work as a vapor retarder. So we need to make sure that it's installed properly if we're making it. Again, that question of, is it there and does it work? So this is the chart, the table that tells us how we can get to a class 3 vapor retarder. In climate zone 5, you can have vented cladding over wood structure, other types of vented cladding, or you can have some level of continuous insulation. And what that continuous insulation on the exterior does is warm up that first condensing surface there. So it's nice because at building at a level of 3 air changes, which is the code requirement in climate zone 5, there you're going to have some level of air leakage into those assemblies there. So in order to ensure that that vapor stays in its vapor state and has the ability to dry out over time and not condense, we need that exterior continuous insulation or some type of vented cladding to promote that continued drying to the outside there. The problem with the idea of vented cladding is that the code doesn't quantify the minimum airspace that is needed. So groups like Building Science Corporation and other building scientists out there have demonstrated that 3/16 of an inch is all that we need for that ventilated cladding. We tried to put a proposal into the 2021 IECC. It didn't pass, so we'll continue to do that. Right now, this language that's been crossed out down here, that's how they're defining the vented space there. So, I don't know, the different jurisdictions are going to interpret that differently there, but just know that all you really need is at least 3/16 of an air gap there to the outside. And then class 2 vapor retarders, there are also some requirements in terms of adding continuous insulation in certain climate zones in order to use a class 2 vapor retarder there. So they have a whole table associated with that. And you'll see some jurisdictions in dry climates really that have basically gotten rid of the class 1 vapor retarder requirement or have modified these tables to make it easier to build more forgiving assemblies there. So if you're involved in code compliance or code adoption in your particular jurisdiction, this might be something that you're looking at. So ultimately, vapor control also means drying control. How are we going to prevent our systems from getting wet, and how are we going to let them to dry, ideally in both directions, but at least in one direction? In climates like I'm at here in climate zone 5, we always want to have drying potential to the inside of our assemblies here. So let's keep that in mind. And the code is really helping us understand that. But we have to build our assemblies to allow that drying potential there. And the code is guiding us. Okay, so let's look at the air control layer here. Again, that belt and suspenders approach, but the code doesn't describe anything more than continuity as a principle of air barriers. So we also need to think about the strength, the durability, and stiffness of the air barrier. So we're really kind of leaning towards, at least when we're talking about adding supplemental air barriers, adding rigid air barrier materials. In Colorado, we often see thermal ply as a material that's added to get that continuity of the air barrier system, maybe behind a tub on an exterior wall or on the attic side of a knee wall or behind a fireplace, for example. So continuity is a huge aspect of that air barrier system. Again, it's defined basically as a combination of materials, an assembly of things. That belts and suspenders approach is what the air barrier is looking at here. So the primary function is to enclose fibrous insulation. So we're trapping that air pocket. We're getting that true R value of the material. So you'll hear about that idea of 6-sided enclosed cavity insulation, especially when it's air permeable insulation. We're getting better air control, we're getting better thermal control, and we're getting moisture control here. So that's the building science principle, is control and predictability, and control of airflow, thermal flow, and moisture flow in our houses there. The energy code tells us we have to have all these things on our construction documents. And what's been added in the last few code cycles are these air barrier details. Details like installing that air barrier behind the tub, or getting the air barrier up to the bottom quarter of the truss and the exterior wall so that this whole drop ceiling is brought into the conditioned space of the house, which means that we have to have proper sequencing. We have to have the framer on board to know that they are responsible for installing that air barrier and then doing the overframing and sequencing it properly. What you'll see is that about 90% of the air barrier details that are defined in the air barrier and air sealing table are really the responsibility of the framer. This table is just like the Energy Star thermal enclosure checklist that is telling us if we deal with these areas of the code. The components are listed on the left-hand side, the requirements for air barriers in the middle and air sealing, and then the installation requirements on the right-hand side here. If we understand this table, you should have absolutely no problem achieving 3 air changes per hour there. So again, it comes down to the question of, is it there and has it been installed so it actually works? So you'll see the picture on the upper right-hand picture there. The air barrier isn't tall enough. It doesn't go to the underside of the lip of the tub. So we don't have continuity there, for example here. And then we're going to test it. So the code is all about building air tightness. They created this, I wouldn't say it's an exception, but you see that the maximum air leakage rate shall not exceed 5 air changes per hour. A lot of people think when they read that that's an allowance to build a leakier house. The reality is that this is only is an allowance in sections R405 and R406 for potentially trading off a leakier house for more insulation somewhere else in the envelope. Generally, I've never seen a trade-off go that way, so I'm not that concerned about it. But you'll get to this section that is allowing some leakier buildings for attached housing and smaller dwelling units. And you'll also see that the air leakage metric has moved from an air change per hour metric, a volumetric measurement, to a CFM per square foot of enclosure area. So you add up the square footage of the 6 sides of the box, you get your total enclosure area, and you can't leak more than 0.3 CFM per square foot of that enclosure area. The reality is I'm not sure we're going to need this metric much anymore for attached housing, because if you look at the what's called the BXUV guide for building the shaft liner area separation wall that's used in townhouses and duplexes, you're now allowed to air seal that 3/4 inch gap between the gypsum firewall and the supporting framing there. So make sure you look at that if you're building townhouses or duplexes. And then we get to the prescriptive requirement, which is still at 3 or 5 air changes, depending on your climate zone there. So again, there is that kind of relaxation if you're using the performance approaches, the true performance approaches, energy modeling for the simulated building performance or energy rating index approach. But the code is really focused on that sound building science principle and mantra: build tight and ventilate right. And it's saying, yes, we can control the holes, and that air barrier, air sealing table is telling us where we need to air seal, and basically that we have to air seal everything around the building envelope. But we can really control these driving forces or these pressures that happen in our houses. So if we're going to control the airflow in our houses, we need to control the holes. We need to tighten up the building envelope. So build as tight as we can and then ventilate the house there. I'm going to skip this and get into the ventilation trigger here. You'll see in the 2021, it's no longer linked to air tightness. You basically just have to provide mechanical ventilation. The assumption is that building at 5 or 3 air changes is tight enough to begin needing mechanical ventilation systems. You're allowed to do supply ventilation, exhaust ventilation, or balanced ventilation strategies in order to make that house work. There are advantages and disadvantages of all the systems there. You need to pick a climate-specific one that works for you and your particular design there. Okay, our last control layer here, we'll cruise through in our last 5 minutes, which is the bulk water control layer. It's all about draining the water down the building and ultimately getting it away from the site. You do have to go to the IRC to see where it's talking about this control layer. But it's really talking about that weather-resistant barrier. You can also look at the roofing sections to talk about how to dry in your roof and whatnot and drain that water off. But you can see one layer of water-resistant barrier shall be applied over the studs or sheathing on all exterior walls with flashing as indicated to provide a continuous water-resistant barrier behind the exterior wall veneer. The water-resistant barrier material shall be continuous to the top of the wall. So why I often say that Tyvek or other fabric type weather resistant barriers work really well as weather resistant barriers, but they aren't always installed as air barriers there. So again, we're going to get that belt and suspenders approach benefit from the water resistant barrier. But unless we also seal that barrier to the top and bottom of our assemblies, we're not going to get the true benefit of it as an air barrier there. But it works well for this bulk water control here. The other thing I wanted to point out was this part specifically for dry climates. It says that water-resistant barriers shall be a 2-layer system when you're using stucco, for example. The individual layer shall be installed independently such that each layer provides a separate continuous plane. And what they're getting at there is that stucco is going to adhere to one of those layers there. What they really should say is that you should have a sacrificial layer. It doesn't have to be a true water resistant barrier, but it has to be a sacrificial coat that the stucco can, or lick and stick stone or any type of mortar-based stone can adhere to, so that you have the continuity of the drainage plane behind that system that becomes the sacrificial coat for the mortar there. Then down here it says the water resistant barrier shall be separate from the stucco by a layer of foam plastic, non-absorbing layer, or a designed airspace here. So you can use products like the Keen system that creates a designed airspace, Dorkin products, different products out there that create that design airspace here. And really that's important in any climate zone. It just happened to be an issue here as well. And then there's some issues in more moist and marine climates that you can look at as well. And then the IRC continues to talk about flashing membranes, that they shall be applied single fashion in a manner that to prevent the entry of water in our system. So we have all kinds of new products with the zip sheathing or the quick flashing materials. How we integrate them into the weather resistant barrier to make them work is super important. But the code helps give us guidance around windows and doors and other penetration, that the flashing of openings shall extend to the surface of the exterior wall finish or to the water resistant barrier, so that we get that clear drainage all the way down and then ultimately out and away from the house. Kind of the biggest bang for the buck is if we can get builders to adopt this idea of a vented rain screen. Regardless of the product that we're using to clad our houses, moisture bypasses it, and we need that vented space to promote drying, to allow us not to have to install a class 1 vapor retarder, and to promote drainage down and out behind that cladding system there. So the single big thing that we could promote as a group is the use of that vented rain screen. There are a variety of different ways to get it done here, but we need to get it done. And this one on the left here kind of gives you the idea of the sacrificial coat that stucco will need to adhere to, but to maintain that gap and the weather resistant barrier underneath it there. Again, there are different ways of doing it, but ultimately from a bulk water management perspective, we're preventing, and really understanding all the control layers is we're trying to prevent the wetting of our assemblies exceeding the ability for our assemblies to actually dry. So this kind of hygrothermic balance is what we're talking about. Keeping that balance so that wetting mechanisms don't overcome drying mechanisms, that we have this balance in our assemblies there. So ultimately, from a biggest bang for the buck here, energy efficiency, putting in better glass, understanding weather-resistant barriers, understanding the value, true value of continuous insulation and why the code is moving steadily to get more insulation outbound in our assemblies there. That's what we're trying to promote through the codes and code adoption here. So the code provides a lot of flexibility. The code is trying to protect the building thermal envelope and ensure that we think of the building thermal envelope as an assembly of things and kind of that belts and suspenders approach. The building science that's wrapped into the code is all about creating control and predictability, and that's wrapped into a variety of sections in the energy code. And remember that the codes are a family of codes. They work together. So we do move from the energy code to the IRC, to the IMC, to the different codes that are there. And then we ultimately are designing for modern day comfort, durability, and efficiency. And that gives us the synergy, which is that idea of systems thinking that is all baked into building science. And synergy is basically where two or more things are coming together to achieve what we couldn't achieve before. So we really need the codes to help us understand that. So I just went over our time, but I'm happy to stick around if anyone wants to talk or ask questions. And thanks so much for having me.
Yeah, Robbie, thank you so much. That was great. Particularly helpful as the 2021 IECC updates. What's your take on, I think what the code is telling us in a lot of the northern climates is we're going to go to R60 attic insulation, but are we not going to see a trade-off there where people use an energy heal truss with R49 insulation continuous to the edge? And if that's the case, why not codify an energy heal truss?
Yeah, it's a good question. So that allowance to go down to an R49 is only allowed when you are using the R value table compliance option. If you don't want to use a raised hill truss, you have to go to a software modeling compliance option there. And so still a lot of people don't want to use a raised hill truss there because of the expense and whatnot. And that's probably why they're not codifying the raised hill truss there. But in implementation, you're also seeing a lot of jurisdictions not enforcing the raised hill truss in when they're using the R value table for compliance. So it's a big thing. What you are going to see in the 2024 is it's going to move back to the base requirement of R49 from R60. You've pretty much hit that diminishing return on your investment at around R50, R49 there. So you'll see it go back in the 2024.
That's what I'm hearing too. Robbie, you just got back from summer camp. What was the exciting talk out there? What did you learn? What did you pick up?
Yeah.
Tell us the future.
Yeah. Well, from a code perspective, it really wasn't talked about a lot. Yeah. But there, continued talk as usual about moisture and moisture issues in houses, and the code is obviously dealing with that. Also about healthy air and ventilation issues in our houses. A lot of talk about kind of the direction of passive house and in Massachusetts and other states that are starting to adopt passive house for code compliant in multifamily buildings there.
Robbie,
lots of good conversations.
Yeah, Robbie, one thing, I think the new 2021 is going to require ERV, HRV in climate zone 7 and 8. Yes. And I think directionally what we're hearing is that's going to move to climate zone 6 in the 2024 code. Of course, here in
Yeah.
Minnesota, we already have it, but is that your understanding as well, that ERV,
Yes.
HRV will be required?
Yes. Yes.
Great. Great. Well,
yeah, I mean, yes. I mean, the code in general talks about balanced ventilation. So there are other ways of creating balanced ventilation, but you're correct, in climate, they do specifically call out ERVs and HRVs in those other climate zones.
Awesome. Well, write down Robbie's contact information and email address. He's a wealth of information and one of the really great folks in this industry. Robbie, thank you for spending some time with us here today.
Great. Well, thanks so much for your time, and I appreciate the opportunity.
Okay. See you soon.
Okay. Bye-bye.
Bye.